Today we start our sixth lecture. This is the second lecture on informed search. In the last class, we looked at the algorithm A star. We looked at the different properties of A star. Today, we will continue with A star and talk about another algorithm called ID A star. The objectives, the instructional objectives of today's lecture are the following. In this lecture, the student will learn the algorithm ID A star, which is an algorithm for informed search. They will be able to analyze the space and time complexity of ID A star, and they should be able to understand the difference between ID A star and the algorithm A star. The student will also get an introduction to some of the restricted memory search algorithms like RBFS, that is recursive best first search, as well as MS star, but we will not cover these algorithms in great detail. We will also discuss briefly some local search algorithms like hill climbing as also simulated annealing. The students will get a brief idea about these algorithms. They will also have an understanding about the properties of such algorithms. So, let us just quickly go over A star search. So, A star, as we have seen in the last class, is a best first search where we use the function fn equal to gn plus hn to order the nodes for expansion. The nodes are expanded according to their increasing f values. We have also seen that in case hn is admissible, then search will find the optimal solution. A heuristic function hn is said to be admissible if it underestimates the cost of any solution which can be reached from the node. So, to briefly recapitulate algorithm A star, we have two lists, open and closed. If we want to deal with a state space containing repeated states, and we want to ensure that a particular state does not get expanded multiple times, we need to keep along with the open list another list called closed, which consists of nodes which have already been expanded. Open is the list of nodes on the frontier of the search tree. Initially, closed is empty and open has a single node, the start node, and the path associated with the node is an empty path. Then the algorithm A star executes this loop. While open is not empty, certain things are done. So, in this loop that we will see in the next slide, we try to see if we can find a path from the start node to a goal node. If we do not find such a path in this loop and we have no more nodes to expand, that is open becomes empty, the algorithm should return failure. Now, this is what we do in the body of this loop. We remove from open the node NP whose Fn value is minimum. N is the node, P is the path associated with the node, N is that node whose Fn value is minimum. We put NP on closed because it has been expanded. If N is a goal node, we return success and we return the path P, which is the path associated with this node. Now, otherwise we find all edges coming out of the node N, that is edges connecting node N with some other node M. Suppose there is an edge E connecting N with M whose cost is C. Now, we consider this node M, this state M. If M is already on closed with a path Q and our current path P concat E happens to be cheaper than the cost of the path Q, then we will like to consider this current path as the best path to M. If Q is cheaper, we throw away our current path. But if MQ is enclosed and the current path is cheaper than Q, we remove the node M from closed and put the new node, the current node whose state is M, whose path is P concat E, we put this node on open. Otherwise, if it is the case that a node M is on open already with a different path Q and the current path cost is cheaper than the cost of Q, then we replace Q with the current path P concat E. Otherwise, if M is not on open and not on closed, we put M P E on open. Okay. So, this is expanded, this algorithm is expanded in this section. Now, let us see, in the last class we have done an analysis of the algorithm A star, and we have seen that A star is an optimum algorithm. That is, if there is a path from the start state to the goal state and then S star is guaranteed to find the optimum path, an optimum path to the goal node. We have also seen that all algorithms that use the same heuristic function h n, A star is an optimally efficient algorithm. A star is also complete, that is, it finds a path if one exists, and we will also discuss today that the number of nodes searched by A star is exponential in the worst case. So, if we model the search space, we will not do the full analysis in this class, but we will just state the result. If we assume that the search space is a uniform BRE tree and there is a unique start state S and one goal state G whose distance from the start state S is capital N and every arc has a cost of 1, then we can show that the number of nodes expanded by A star is exponential in n unless the heuristic estimate is logarithmically accurate. That is, suppose H star n is the actual, suppose H star n is the actual cost from n to the goal, optimum cost from n to the goal, and suppose H n is our estimate. If H n minus H star n is less than or on the order of log of H star n, then the heuristic is said to be logarithmically accurate, and in this case A star does have polynomial complexity on such a search tree. However, in most cases we can say at most that practically the heuristic functions that we can get, they are at most proportional to H star n. That is, the error is proportional, error is not logarithmic, and in those cases A star has exponential complexity. Now, so A star has exponential complexity. So, A star, as we have seen, tries to improve upon general breadth first search by using this heuristic function to restrict the number of nodes being expanded. However, this restriction is not good enough because the complexity of A star is still exponential. If we get a better heuristic function, then the number of nodes expansion can become less. So, A star still can take a lot of time on a reasonably large problem, but even worse than the time complexity of A star is the fact that it becomes difficult to use A star even before the time runs out, because the size of the open queue becomes too large, because the space complexity of A star is the space required for storing the open queue, and in those cases where we use a closed queue, we also have to store the closed queue. Now, the solution, so that A star does not have this bottleneck, or search algorithm does not have this bottleneck, is to have a search algorithm which uses less space. Now, we will discuss an algorithm IDS star, which is an iterative deepening algorithm, and IDS star requires less space. We have already talked about iterative deepening search, which is basically a depth first search which does a level by level expansion of the search tree. And we have seen that iterative deepening depth first search has a space complexity of order BD, where B is the branching factor and D is the depth of the tree. Here D is at most the capital N, which is the cost of the solution. So, if we use iterative deepening search, we can have an algorithm which works in linear space. However, iterative deepening A star is actually slightly different from iterative deepening search, actually very similar, where the nodes to be expanded in a particular iteration depends on the f value of the nodes and not on the level of the nodes. So, in iterative deepening A star, the cutoff for nodes expanded in an iteration is decided by the f value of the nodes. So, we fix a limit of the f value, and in an iteration we only expand those nodes in a depth first manner whose f value is less than this less than or equal to this f limit. In the next iteration we increase the value of this limit. Now, let us look at iterative deepening A star. So, in iterative deepening A star is a depth first iterative deepening search, but the depth bound used is an f limit. So, we start with the initial limit as the f value of start. So, there is a mistake here. So, we use a f value of start as the initial cutoff or initial limit. Then with that limit we do a depth first search, and in doing this depth first search we prune any node if f of that node is greater than the value of f limit. So, after the current iteration, the next f limit is chosen to be the minimum cost of any node that was pruned. Now, let us try to illustrate iterative deepening A star on the following graph. We have 6 nodes A, B, C, D, E, F. Initially, we fix a f value equal to the f value of the start node. Suppose the start node is A. So, and suppose the f value of the start node is 15. So, using the f limit as 15, we do a depth first search in which A, B and E are expanded. Now, C and F were the nodes which were pruned in this first iteration, and suppose the f value of the minimum of f out of f value of f and f value of C, the f value of C was minimum and it was 21, and the next iteration we will use the f value of 21 and we will expand this we will do a depth first search with this f limit equal to 21, and in the next iteration C was the node pruned with a particular f value. We will set that equal to the f limit and do the next iteration and so on. Okay. So, this is the schemata of iterative deepening A star. So, it is basically iterative deepening search, where search is pruned when the f value of a node exceeds the current f limit, and the minimum f value of a node pruned is used as the next value of f limit. Now, let us look at the properties of the algorithm IDS star. IDS star is complete and it is optimal. It is complete because it will find a solution if one exists. It is optimal because the first time it expands a goal node, it would have found an optimum solution to it. The space usage is proportional to the depth of the solution. Each iteration of IDS star is a depth first search. So, it requires only space equal to B times D, branching factor times the depth of the tree. So, space requirement is linear. Now, you note that what are the extra nodes which are expanded in every iteration? They are those nodes whose f value is immediately just greater than the f value of the nodes in the previous iteration. So, the number of nodes expanded in subsequent iterations, the nodes expanded at the nodes with increasing f values, right, and hence IDS star is an optimal algorithm. But so it is obvious that IDS star expands more nodes than A star because certain nodes are expanded more than once. Now, how many more nodes does IDS star expand compared to A star? That depends on the number of unique values of Fn, right. So, if it is the case that between two iterations, the extra number of nodes expanded is large, then IDS star is fairly efficient in the number of nodes expanded. But consider the case when every node has a unique f value. In that case, at every iteration only one new node will be expanded, and in this case IDS star will expand the square of the number of nodes in A star, which we will see. So, space required by IDS star is OBD, number of nodes expanded relative to A star. In 8 puzzle, there are few values of f, and the number of nodes expanded by IDS star is very close to the number of node A star expands. In F, suppose in 8 puzzle, we use as Manhattan distance or the number of misplaced tiles as the heuristic function. The number of values such a heuristic can take is very small. The number of misplaced tiles can be at most 8, right. So, the total f value is actually also not very large. As a result, the number of unique f values is small. So, IDS star tends to expand a large number of extra nodes in every iteration, and the number of iterations is equal to the number of distinct f values. However, consider the travelling salesperson problem, where we have a graph of n cities, and the objective of the travelling salesperson is to start from a city, traverse all the cities exactly once and come back to the starting city. Imagine that every distance between a pair of cities is a different real value. Okay. In this case, it is possible that each f value is unique. So, IDS star will expand one new node in every iteration, and the number of nodes expanded would be in the first iteration 1, second iteration 2, third iteration 3, and the last iteration the number of nodes expanded will be equal to n. So, the total number of nodes expanded equal to big O of n square, where n is the number of nodes A star expands. So, we see that IDS star can expand at most a quadratic number of nodes expanded corresponding to A star. However, in other situations like 8 puzzle, IDS star would expand only a constant factor more nodes than A star would expand. Also, we see that because in IDS star we are using basically a depth first search, we cannot avoid repeated node expansion. To IDA star does expand duplicate nodes in cyclic graphs. If a graph contains cycles, IDA star may repeatedly IDA star will not be able to detect the cycles and it will expand those nodes repeatedly. But the main advantage of IDA star is its linear memory. For example, 15 puzzle is a problem. It is similar to 8 puzzle, except that the problem is on a 4 into 4 grid. There is one empty square. So, 15 puzzle, if you run A star on 15 puzzle, it will take a huge amount of time to solve and a huge amount of memory. 24 puzzle possibly you cannot solve in A star using normal resources because of the huge space requirement and space requirement. However, you can use IDA star which does not need to keep this open queue, which will be able to solve 8 puzzle and 15 puzzle. Now, IDA star uses very little memory. It only uses linear memory and it may expand up to a quadratic up to n square nodes if A star expands n nodes. Now, the idea of memory limited heuristic search algorithms is to use the available memory optimally, so as to have a more efficient algorithm which reduces node expansion. Several such algorithms have been proposed and we will briefly mention these algorithms. Recursive breadth first search or RBFS is an algorithm which actually uses only linear space, but it is often better than IDA star because it mimics best first search. RBFS keeps track of the F value of the best alternative path available from any ancestor of the current node. So, whenever RBFS is a linear memory algorithm, it does not keep track of all the nodes, but those nodes that it has expanded and the algorithm chooses to forget, the algorithm backs up at a node the F value of the best successor of that node. If the current node exceeds, so at a particular node we have an F value, current F value, and we also know what is the second best F value based on what we had expanded earlier. When the current F value exceeds this alternate F value, then RBFS will explore this alternate path. So, we will not discuss the algorithm in detail. We will mention another algorithm called MA star and it is a related algorithm SMS star. So, these are restricted memory best first search algorithms that utilize all the memory that is available. The algorithms execute best first search. When memory is available, it does normal best first search. When the memory becomes full, the worst node is dropped and the value of the forgotten node is backed up to the parent. When the node is dropped, the value of this backed up node is value of this dropped node is backed up to the parent. Next, we will briefly talk about, so we have seen systematic search algorithms, depth first search, breadth first search, best first search, A star, IDA star, bidirectional search and so on. And we have seen that A star and IDA star and such algorithms or even RBFS, they use some heuristic function to restrict the number of nodes that are expanded. However, under most natural types of heuristic functions that we can obtain, these search algorithms have exponential time complexity. There are situations where it is not possible to use such algorithms to get the best solution to a problem. Local search is a class of local search methods are used in a class of search algorithms where we need not have an optimum solution. There are problems where we need a solution and we can get a solution which may not be the optimum solution, but we can get the solution in limited time. Local search methods work on formulations where every configuration we have a complete state. So, local search does a search on complete state formulations. So, in local search typically a small number of nodes, a constant number of nodes are kept in memory, and these nodes are all configurations of the entire state. These states are perturbed to get the next state. Local search is useful for two types of problems. One, it is useful for solving optimization problems. In those optimization problems where it is often easy to find a solution, but hard to find the best solution. Consider the traveling salesperson problem in a fully connected graph. It is easy to get one solution to the problem because any permutation of the cities is a solution, but it is difficult to get the best solution because there are n factorial such permutations and we do not know an efficient way of finding the best permutation in polynomial time. So, in TSP the objective is to find the optimum configuration, which is difficult to find. We do not know a good algorithm to find it, but if we just want to find a solution, it is easy. So, many local search algorithms use iterative improvement, and we can try to get a solution and get improvements to the that solution. Secondly, there are problems where these optimization problems like TSP, we do not have to keep track of the path to the solution. When we have the solution, we immediately know the path. In TSP, we do not have to keep track of the path. Local search is ideal for such cases. In problems like 8 puzzle, it is important for us to know how we, so the final state does not give us any information about the path. The solution path has to be obtained. Local search is not very good for such problems. For problems like TSP where the path is not important, local search is very useful. Another example of a problem is the n queens problem, where we have a n by n chess board and we have to put n queens on the board so that none of the queens are attacking each other. For this problem, once we have the final configuration, we know the solution. So, n queens problem, it is not obvious how we can get a solution. So, we can define n queens as an optimization problem, which we will see. So, the basic idea of this iterative methods is to start with a solution and improve it so that we can get a better solution. Example is the n queens problem. We have to put n queens on the chess board. So, in this case we have to put 4 queens. So, what we can do is that we can start with any placement of the 4 queens on the board, but if we place the queens like this, obviously there are many conflicts. So, we can reformulate our objectives as saying we want to have a board with 0 conflict, or we can say we want to minimize the number of conflicts. That is, we want to minimize the number of pairs of queens which can attack each other. Okay. So, we start with this state where this pair is attacking each other, this pair is attacking, this pair is attacking, this pair is attacking, this pair is attacking. and then we move to this configuration where this is attacking, this is attacking, this is attacking, and then we move to this configuration where this pair is attacking each other and none of the other pairs attacking each other. So, we have reduced the number of conflicts between queens. So, hill climbing is one local search method. It is also called gradient ascent or gradient descent. In hill climbing, the idea is that we start with the current configuration and we move to a new configuration to maximize the value, right. For example, in queens, our objective is to minimize the number of conflicts. So, we start with an arbitrary configuration and we move to a new configuration where the number of conflicts are reduced. So, we find from the current configuration different configurations of the different neighbors and we move to that neighbor which has the minimum number of conflicts. So, the neighbor which is best, that is why it is called hill climbing. We go to the best neighbor and we continue until we get to a state where all the neighbors are worse than this state. So, we can talk about hill climbing when we are either minimizing a value function like minimizing the number of conflicts or maximizing a value function. They are symmetrical. For example, in 8 queens, we can start with an initial state and we can define our successor function as moving a queen to another square in the same column. And the cost associated with the configuration is the number of pairs of queens that are attacking each other. We want to minimize these pairs. Now, we can, this is a schematic diagram of the state space of hill climbing. So, we are starting at a particular position and we want to move to a neighbor whose value is larger. Now, depending on which initial state we start from, we can get stuck in local extremum. Suppose we start from this position. Suppose we start from this position and then we find that this is the best neighbor and then we find this is the best neighbor. So, we can move until we get here whose neighbors are all worse than this. So, this is the solution that we have obtained and this also happens to be an optimum solution. But suppose you start from here. If you start from here and then if you move to the best neighbor and then its best neighbor and then here you will get to this position where all its neighbors are worst, but nevertheless it is not the optimum solution to this problem. So, if we use hill climbing, because it is a local search method, we can get stuck at a local extremum instead of always landing up at the global optimum. So, we can compare our state space to that of a physical system that is subject to natural interaction and we can look at the analogy of our value function to the overall potential energy of the system. On every updating, we have delta E less than equal to 0. So, this is the change in potential energy. Now, in this schema of the state of the value of the state space in this state, this is our global optimum. This is our global optimum and we see that this, if we this is a this diagram is for a minimization problem where C is the global minimum. And what we see is that if we start at any of these positions, we can get to the local to the global minimum. So, this region is the region of attraction, basin of attraction for C. So, if our initial starting is between these two lines, then we can reach this global minimum. However, if our initial starting position is somewhere here, we cannot reach this global minimum. We will instead settle to a local minimum. Now, so in local search, we cannot guarantee global minimization because of existence of many local minima in general. Now, the question is, so if you use hill climbing, you cannot avoid this problem. How can you at all avoid this problem? So, let us look at an example. Suppose this is our the value function at different states, and this is the starting point. Now, if we start at this starting point and we use hill climbing or hill descending, this is the direction of steepest descent, and this is where our ball will roll until it settles at the local minimum. So, this hump is acting as a barrier to the local search, and our ball is settling at the local minima instead of going to the global minimum. Now, if you want to avoid this problem, we must let our ball also go in the suboptimum direction in order to get to the local minimum, to the global minimum. It may be necessary to climb the hill at certain points, even though we want to reach the deepest valley. So, occasional ascents are required, so that the ball can get over this hump and settle at a minimum, which may be global or local. Now, so ascent will help escape the local optimum, but if we allow ascent, ascent may also help the ball get past the global optima after reaching it. So, we can avoid this by keeping track of the best state. So, if we start from here and we also allow ascents, and then we keep track of the best state reached so far, we may be able to identify the best state which this ball has reached. So, what we do in simulated annealing, simulated annealing is an algorithm which avoids some pitfalls of hill climbing, and the basic idea is this. From the current state, we pick a random successor state. If that successor state has a better value than the current state, then we accept the transition. If it has a worse value, we do not give up, but with a probability we accept, with some probability we accept a worse transition. So, if we get a successor whose value is smaller, value is worse, we flip a coin and accept the transition with some probability. So, we sometimes accept non-optimal solutions. So, initially with higher probability we accept non-optimal solutions. As time passes, with smaller probability we accept non-optimum solutions, so that we allow our ball to settle to a minimum. So, the details we will not talk about. There are other local search algorithms like genetic algorithms, which will also is beyond the scope of this lecture. So, what we will do now is discuss the questions of lecture 4, the answers to the solutions to the questions of lecture 4. This was the question. You are given a full 5-gallon jug and an empty 2-gallon jug. Your objective is to fill the 2-gallon jug with exactly 1 gallon of water. You use the state space formulation like this. A state is represented by a pair x y, where x is the number of gallons of water in the 5-gallon jug, y is number of gallons of water in the 2-gallon jug. Initial state, first bottle jug contains 5 gallons, second jug is empty. So, 5 0. Goal state star comma 1. that is the second jug must have 1 gallon. The first jug can have any value, we do not care. So, for this problem you have to create the search tree and discuss which search strategy is appropriate for this problem. Let us look at the solution to this problem. Now, this table illustrates the different operators and the effect they have. So, these are the operators: empty 5 gallon jug, empty 2 gallon jug, transfer from 2 to 5, transfer from 5 to 2, transfer from 5 to 2 partially. Now, empty 5, these are the preconditions. Empty 5 can be always used, and as a result you move from the states x y to the state 0 y, because this jug becomes empty. Empty 2, that is the empty 2 gallon jug, if you apply it on state x y, you get the state x 0. 2 to 5 is the operator to pour 2 gallon into 5 gallon. If you start with x 2, you get to x plus 2 0. So, pour 2 gallon into 5 gallon. So, this 2 gallon it comes here. If you pour from 5 to 2, you can apply this only if x is greater than 2, that is the 5 gallon jug initially has more than 2 gallons of water. In that case, x 0 will give you x minus 2, 2. 5 to 2 partially you can apply when y has less than 2 gallons of water. In that case, 1 y will become 0 y plus 1. So, you pour the partial 5 gallon into 2 gallon. So, this table shows the effect of all the transitions. Now, these are the different states, different pairs of states 0 0 0 1 0 2 1 0 1 1 1 2 2 0 2 1 2 2. These are all the states of our jug problem. Now, the empty 5 takes you from 5 2 to 0 2, from 4 2 to 0 2, 2 2 to 0 2 and so on. It also takes you from 5 1 to 0 1, 3 1 to 0 1, 2 1 to 0 1, from 5 0 to 0 0 and so on. The next operator is empty 2, which takes you from 5 2 to 5 0, 4 2 to 4 0, 5 1 to 5 0, 3 1 to 3 0 and so on. 2 to 5 takes you from 3 2 to 5 0, 4 1 to 5 0, 2 2 to 4 0, 3 1 to 4 0 and so on. 5 to 2 takes you from 5 1 to 4 2, 5 0 to 3 2, 4 1 to 3 2 and so on. 5 to 2 part takes you from 2 2 to 2 0, 2 1 to 2 0 and so on. Now, let us see how, so from this state space we have to find the solution from the starting state to a goal state. So, let us see how we can do that. So, this is the state space that we start with, and from this yellow box is our starting state. And now, if we do a search, we find that the optimum solution will go from 5 0 to 3 2, then from 3 2 to 3 0, from 3 0 to 1 2 and from 1 2 to 1 0, from 1 0 to 0 1. So, we have a solution which requires 5 steps. Now, let us see which search algorithm is appropriate for this problem. Depth first search is not appropriate because, as you can see, the state space is a graph and there are many repeated states. So, depth first search is not appropriate, breadth first search is appropriate. Now, let us look at the second question from lecture 4. You are given the following graph. Starting from state A, you have to execute depth first search and reach the goal node G. and you have to show the order in which the nodes are expanded. And the third question was, you run iterative deepening search on the same graph. We will see the solution to this problem. So, this is our this is our graph, and this is the search tree that we obtain when we look at these states. After we unfold this graph, this is the tree that we get. So, if we do depth first search, initially our list open, that is fringe, contains the node A. Then A is removed from the fringe, B and C are expanded and put in open. Open is a stack when we do breadth first search. Then B is removed from the front of the stack, and D are added to the front of fringe. Then the first node from fringe, that is D, is removed, and its successor F is added to the front. Then F is removed from fringe, its successor H is added. Then H is removed, and then E is removed, then C is removed, its successors D and G are added in the beginning. Then D is removed from the front, its successor F is added, F is removed, H is added, H is removed, G is removed, and we have found a goal state. Okay. By depth first search, this is the order in which the nodes are expanded: A, B, D, F, H, E, C, D, F, H and G. Now, let us run iterative deepening search on the same state space. Initially limit is 0, so we can expand A only. Then we set limit equal to 1, and we get this tree which is expanded in a depth first manner, that is A, then B, then C. So, this illustrates the second iteration of IDS. In the third iteration, limit is set to 2, and in this iteration, this tree will be searched in depth first manner. And when we do search this tree, we get first A is removed from fringe, and then B and C are added, B is removed, D and D, then D is expanded, E is expanded, C is expanded, D and G added to fringe, D is expanded, finally G is expanded. And then we have found a goal node in this iteration where limit is equal to 2. Okay. Now, we will just look at the questions that we had posed in lecture 5, and the solutions to these questions as well as the questions of lecture 6 we will discuss in the next class. For lecture 5, these are the questions. You will be given a following search space. This search space is specified by this table. Please note down, in this state space there are 7 states A, B, C, D, E, F, G. For state A, there is a edge to state B with cost 4. There is an edge from A to C with cost 1. There is an edge from B to D with cost 3, B to E with cost 8, C to C cost 0, C to D cost 2, C to F cost 6, D to C cost 2, D to E cost 4, E to G cost 2, F to G cost 8. Okay. So, given this state space, you are required to draw the state space of this problem. Then we assume that the initial state is A and the goal state is G. For this state space, you have to trace each of the following search strategies to create a search tree and to find a path from initial state to the goal state. So, you are required to use this state space and run uniform cost search, greedy search as well as A star search. For each of these 3 algorithms, you will trace their execution and find the order in which the nodes are expanded. At each step of the search algorithm, you have to show which node is being expanded and the content of the open list or fringe. You also have to report the eventual solution found by each of the algorithms and the solution cost that was obtained. The next question from lecture 5, you are required to write the algorithm for bidirectional search using pseudocode. We discussed bidirectional search in the last lecture, but you will have to provide the pseudocode for this algorithm. You assume that each search is a breadth first search and the forward and backward searches alternate and they expand one node at a time. Okay, is that clear? Third question, you have to find the time complexity of bidirectional search, assuming that the test for connecting the 2 searches is done by comparing a newly generated state in the forward direction against all the states generated in the backward direction one at a time. So, you remember in bidirectional search, you have to check whether the 2 frontiers of the forward tree and backward tree have met. Suppose you do this check by checking the node expanded in the forward tree with all the nodes in the backward tree, what would be the time complexity of bidirectional search? That is question number 3. Now, we come to the questions from the current lecture, that is lecture 6. For this, the problems for this lecture will be of this type. You will be given a search space. You can use actually the same state space that we gave in question number 1 of lecture 5. In question number 1 of lecture 5, we specified the search space by this table. For the same search space, you have to apply IDS star, and for IDS star you will also require the value of the heuristic function. Assume some values of Hn and apply IDS star on this state space. You have to compare IDS star with A star in terms of time and space complexity in general. So, you compare the characteristics of A star with IDS star in terms of time complexity and in terms of space complexity. That is the second question. Third question, suppose you are using hill climbing to find a solution to the n queens problem. The question is hill climbing guaranteed to give you a solution? Question number 4, if you use simulated annealing, are you guaranteed to find the optimum solution of the travelling salesperson problem? Okay. So, these are the questions of lecture 6. In the next class, we will discuss some of the solutions of the questions both from lecture 5 and lecture 6. That is the end of today's lecture.